Yeesh. Well, physical science time. We're going to talk today about electricity. Electricity. Oh, I'm going to make it so you can actually see what I'm writing, though. Instead of talking, let's all listen as I start the discussion about electricity. Let's start this way. I'm going to raise your hand if you want to volunteer for this, and I'm going to have you describe for me to draw on the board one of the circuits that you did in your lab. We did a lab, right? Everyone in here, maybe not Ethan, everyone except for Ethan did a lab, and you were to have used the materials from that electricity box to make a circuit, and you were supposed to have diagrammed it. Was this fun for you? I thought it seemed like you were having a good time. You were building stuff. Yeah. Would anyone volunteer to describe this to me so I could draw it on the board? Just Will. Will is the only one who volunteered. I guess that's fine. What's up? Will's gonna go, but what? Do you guys need something, or are you just volunteering too? Okay. Okay. Let's all listen. Will's gonna describe his to me, and I'm gonna try to draw it on the board. Okay?
Okay.
Okay. Shh, Raven. Please focus up so that we can all pay attention, okay? Because you're distracting your colleagues.
I made a box saying battery in it.
Okay, and so we usually use this symbol to mean battery in an electrical circuit. You should write this down probably. What does that mean?
Electrical circuit.
No, that symbol means what specifically in an electrical circuit?
Battery.
A battery. Yes. I'm trying to find a reference for you in your book. This is on page 207 if you're looking for that. That's the battery. One of the ends is supposed to be, I think it's the end with the long line represents the positive charge, and the end with the short line represents negative. That doesn't really matter at this point, but I think that's the case. Go ahead with the rest of your...
Okay.
You had a battery.
Then I made a line to open switch, which I
Okay.
draw another box, then a rectangle shooting out.
Someone in the comments is going to at me for not knowing the symbol for switch in a circuit, but I'm just going to I'm going to draw it like this. I think that might even be right. So you had...
There is no comment.
I'm sorry, what?
There is no comments.
Oh, right. The comments are disabled for this video. So you have an open switch here.
Yes.
What does the line represent, by the way? Hey, everyone needs to be taking notes about this. We're going to label this in a second. The line represents some conductive material, usually a wire. Okay? So you have an open switch.
Then I got another wire leading to a motor with a little flag.
Okay, a motor. I'm just going to draw the motor here with a little flag on it.
Yeah.
There we go, a little flag on it.
And then another wire going back to the battery.
Another wire going back to the battery.
Then I have the same thing, but with the switch closed and
Okay.
the flag spinning.
Okay, good. So then if we close this switch, then the what we call the electrical potential from the battery allows for electricity. We could say at this point, we're going to talk about what's actually physically happening here in a second, but we could say electricity is flowing now from, we usually indicate, even though this is not really exactly what's happening, the electricity flows from the positive end of the battery to the negative. We're going to talk about why that's a kind of a misconception, or not even a misconception, but it's kind of a... we do it that way, but we understand that that's not really how it happens. But when it's open like this, there is no flow of electricity. It's not like a river that is dammed up and the water is just sitting there kind of waiting to flow, as it were. It is more like that nothing is happening. The wire here is not closed. There is no conductivity. There's no electrical difference from this end of the wire to this, and so the electricity doesn't flow. But if we close the switch, now the electric current flows, and it flows all throughout this little battery, which there's some complicated gubbins going on in here. There's a brush probably. There's some magnets, and we'll talk about what that means in a little while. I think that actually might be in chapter 8. But when the electrical current is allowed to flow through these magnets, they spin this brush, and the brush spins this flag, and then the circuit is complete by the rest of the battery. What does this symbol represent? I'm gonna write these down. What does this symbol represent? Battery. What does this symbol represent? Wire, or some conductive material. This specifically is a motor. We call this the load. This is the load of the circuit. What the circuit is actually, could you make a circuit where it's just a wire connected to a battery? Like, is this a circuit?
Yes.
Yeah, what does it do?
Nothing.
It kills the battery. That's all it does. It just drains the battery. That's the point of this circuit. What we actually are powering, as many of you mentioned in your bell work, what we were actually causing change in, usually beyond just killing the battery, is to power some load. In this case, a motor. What else could we use? Yeah. Okay, but let's be quiet. Okay. Yes, go ahead, Faith.
So you said that it doesn't just sit there. So would the wire just be part of the battery if it was
Sure, you could consider that to be true. The question was, can you consider the wire, if the switch is open, can you consider the wire just part of the battery? I guess you could. Yeah, there's no reason not to. The wire really is a conduit through which the electricity can flow. And if the electricity isn't flowing, it's nothing. It's not really behaving as a conductor even. Let's switch out the load. This was a motor. What else could we use? A light bulb. And there is a common, actually I think we might, if I'm right, I think we just use a circle with this symbol in it for a light bulb. And then as the current flows through here, the light bulb, what really happens is the flow of electricity excites the atoms that make up this filament. And when they're excited, they produce a lot of heat. And this is for an incandescent light bulb, the old-timey kind of light bulb. It gets really, really hot. It's usually tungsten. It's a filament made of tungsten, a very thin wire of tungsten that has more electrical resistance than the wire. And so the atoms start to vibrate really quickly. It gets really, really hot. It gets so hot that it glows. That's why in the old-timey light bulbs, like we had when I was a kid, they were really more hot than anything else. Your house would get very, very hot if you had all your lamps on with incandescent light bulbs, because that was really what they do, is they produce heat. They happen to glow also because they're so hot, but they don't really, that's not their, I guess it is their main purpose to produce light, but it's not really the primary function they have as a physical object. Fate.
doesn't
Tungsten.
really high melting point?
Tungsten has the highest melting point of any metal, to my knowledge, and that's why it's used, just so that when it gets that hot, instead of melting, it just glows. That's why it's used for that. And it's a very thin filament of tungsten. And what do we call this whole thing? This whole thing is called a what? Circuit. In this case, the circuit is, because of this, closed. This is a closed circuit.
So that means electricity can flow through it.
Electricity can flow through it.
I learned that today.
Good, okay. I don't know that everyone did, but you did. There are two kinds of electricity that we talk about. Does anyone have questions about this circuit diagram? We're going to get back to this. But does anyone have questions about this, so I can erase it? Does everyone have something about this drawn in their notes, the different labels for the different features of it? Okay. What are the two kinds of electricity? Someone correctly, Peyton, identified one of them. What is one broad category of electricity that we talk about? Static electricity. Let's write that down. Static electricity. You've heard of static electricity. I know you have. Static electricity. One reason that I know you've heard of static electricity is that I taught you about it last year in 8th grade science, so I'm a little bit sad and dismayed that you didn't re-identify that. But static electricity comes from the Greek for just to stay. Statos means to stay. It's charge that's just kind of staying or hanging out on a surface. Charge that, I don't want to put hangs out on the board because that makes me seem like an idiot. Charge that that accumulates.
Now I don't even know if that was.
Accumulates on a surface. How can we generate some static electricity? Well, if this were carpeted, which it's not, and I'm grateful for that generally, but if this were carpeted, and I kicked off my shoes and I rubbed my feet along here, and then I went and touched, if I went and bopped Raven, pop, there would be a little discharge of static electricity within there. You understand what I mean? You've experienced this before at your house. Has anyone experienced static electricity before in any capacity? Yeah. Ethan was terribly annoyed by that question, but the rest of us all understand that static electricity is something that's just part of our life. If you've ever been to the gas station, they have a sign that says, touch a metal part of the frame of your car before you touch the gas pump. Why might that be?
Discharge any static.
Just discharge static electricity. I was going to say in the old days, some cars still have cloth seats, but this was especially common back when most cars had cloth seats. But you'd rub your cloth-covered butt. Hopefully it was cloth-covered or some other way covered. But as you get out of your car, you would scoot your cloth-covered butt across the cloth-covered chair. A buildup of static electricity would occur. You'd get out, you'd touch the gas pump, and then everyone for 10 square miles would die because you exploded the gas station. That's an exaggeration. But the static electricity could leap to the gas pump, which could rarely start a fire, and then you'd be in big trouble. Maybe one guy doing that was why they have that sign. Yeah.
I saw an Instagram post. So you know, like the shut off valves, so they shut off all the
Yeah.
valves?
Yeah.
So these guys got like all black suits.
And they did that.
Faces, and they jumped out of the car. They went and slammed on the button. Took off. And the cops and all the fire department showed up, and there's water spraying everywhere.
Oh, you shouldn't do that. That's not a good idea. I wouldn't say.
I thought it was quite funny.
I think you would think that was funny. Yeah.
I would never do it. But
No.
I would watch someone do it.
No. So we have static electricity where, and then in the picture in your book here we have ooh, that's really good. This is very nice. This is I would even go as far as say this is a really sexy drawing of a boot here, and we have it on a surface here. And when objects are just existing in their normal state, they're a mix of positive and negative charges. For every one positive charge, there is a negative charge. There's 1-to-1 ratio, meaning that on average the charge is what?
Even.
Equal to 0. It has no charge. So on average this is neutral, and the same thing with the really, really well drawn and not in any way disturbing drawing of a foot. So when you're just standing there with your really well drawn foot on the carpet, both of these things have
Oh, hold on.
a neutral charge.
You gotta make a little hole so you can put your fingers there and hold it.
Oh yeah, you're right. Sorry. Okay. There is also a leg in here though, so let's draw that. Some hair on it. Okay.
Musty hair.
And also the word "stay." There's a tattoo of the word "stay" just kind of hanging out on the back of the calf. But these both have a neutral charge. Okay, until as one, if we start to rub one on the other. First of all, what kind of, if we have this back and forth motion here, what main kind of energy are we generating there? You remember from maybe 3 chapters ago? What kind of energy is being generated here? Or what kind of energy transfer is occurring here from 3 chapters ago? If we're moving and these two things are rubbing against each other, and thermal energy is friction. So first of all, there's friction. But we had talked about one of the components of friction is that the little bumps that make up these objects are getting like stuck in the grooves, and then they are moving past each other. But other thing that's happening is that electrons, related to the word electricity, yes. Electrons, which have a what kind of charge?
Positive.
Whoops, no one knows the answer. It's a negative charge. Electrons can be transferred from one object to another through contact. So as the well-drawn boot moves on the rug, the electrons might flow from the boot to the rug. And so now, not all of them, it's going to look like all of them, but not all of them. So now, instead of being neutrally charged, the boot has a relative. All the electrons, or some, no, certainly not all. Many of the electrons have flown from the boot to the rug, and so now the boot has a relatively, look at it,
Static.
no,
Positive.
positive charge. The boot has a relatively positive charge, and the rug has a relatively negative charge. Then when this is what we call a static electricity. These both have now a static charge. They both have a charge on their surface. This one has a positive charge on its surface. This one has a negative charge on its surface. So then, as this guy or woman, I don't judge those with hairy legs. As this cat,
Dog.
really, yeah, not specious. As this object moves across the floor, and now what could be over here? This is a cat over here. It's a happy cat.
I was thinking like a
With stripes.
Name is Sir Pound.
As this moves over here to try and step on the cat, just kidding, don't step on the cat. But when this moves over here and now touches the cat, remember what charge does the boot have?
Now the cat's dead because.
Oh, okay, let's try again. Well, remember what charge does the boot have? A relatively positive charge. What charge does the cat have?
Negative.
No. Neutral. The cat has a neutral charge. The cat was not involved in the original. The cat has a relatively positive charge. Or sorry, cat has a relatively neutral charge. But because this has a positive charge, the electrons in the cat, some of them, are attracted to the boot. So some of the electrons transfer to the boot, causing a little. What is this little guy?
That's a lightning ball.
Okay, who said that? No. Who said lightning bolt?
Me.
Lightning bolt is the right answer. This is exactly the same phenomenon as a lightning bolt. What sound does this make when the little cat gets zapped? Yeah, a tiny little popping noise. The cat might also make its own noise, but that's obviously not what I'm talking about. It makes a tiny little popping noise, but that is literally thunder. That is the exact same phenomenon as thunder, just on a much smaller scale. Now, the exact same thing again, but instead of a foot and carpet and the same foot and a cat, let's do it this way. A big old cloud. Now instead of being on the scale of a rug and a boot, let's say this cloud is 1 mile across. And instead of actually literally touching the ground, which I guess in some ways it kind of is, but as it rubs across the ground, the same thing happens. Electrical charge transfers, and I'm not willing to say whether the charge, I think it's usually there's a positive charge in the cloud. Please stop talking. There's a relatively positive charge in the cloud. There's once again a relatively negative charge on the ground. And instead of a cat, instead of a boot, now that same cloud, as it moves over here, or even as time passes, and there's a farmhouse down here, and here's a farmer.
Need a lightning rod though. Big old stick.
Zzzt. Same exact thing. Instead of now going, zzzt, it goes boom, and his life is ruined. He's dead.
No, actually.
The electrical discharge.
No. I know my old teacher at Moral, her dad got struck by lightning
Oh.
2 times. I kid you not, and is still alive.
Yeah. Well, sometimes that happens. Hey, can there be? By the way, when this hush, please. When this static discharge, be quiet, please. Please be quiet. When this static discharge occurs, is it always the same magnitude? Does it always have the exact same effect? To bring it to Taylor's point, even in the example of the boot and the cat, are there different levels of shocking? If Raven has been shuffling around on the floor and he boops you on the nose, are there different levels of electrical shock for that?
Yes.
Yeah. Same thing with lightning. This static discharge. Not quite. There are different levels of this though. The greater the difference in the charge. This is exactly why the boot only has, or the boot touching the cat only has a little zzz, and the lightning has a great big thunder sound, is because there's a difference in magnitude. There's a much bigger difference in the charge difference. Do you have questions about? Shh, please stop talking. Do you have questions about how static electricity and static discharge work? One of the fundamental aspects of this, please write this down, is that in nature we see, at least with the electromagnetic force, that opposites attract. Let's remind ourselves, as the first exercise of this, let's remind ourselves of the 4 fundamental forces of the universe. Which one are we talking about here? What force of the universe is this that we're talking about? Electromagnetic. Do you remember the 4 fundamental forces of the universe? Kesslin, please take notes and stop doing that.
Electromagnetic.
Well, that's not. Let's list them in order. So we're gonna list them. We're gonna list them in order from strongest
To least strongest.
to weakest,
Oh, that's
and then it's the
yeah, no way.
opposite over here from shortest range to longest range. I'm really alarmed by the lack of people writing this down. This is review, but it's extremely important. The strongest and shortest range of the 4 fundamental forces of the universe. You might already have this in your notes. Do you know it? Which one? The strong nuclear force is the strongest. We will talk. I don't actually remember specifically if I've told you guys about this before. I should have. I think I did. But even if I didn't, we will talk about it. We're talking about it now, and we will also talk about it when we get into the chemistry unit, which will be next semester. The strong nuclear force is the strongest and the shortest range, followed by the electromagnetic, followed by the weak nuclear, and lastly, guess? What's the weakest force?
Gravity.
Gravity. It's also the longest ranged. You can remember this with the acronym SUG, or if you prefer SUGE, like sewage without some of the letters. But this is how I have had people remember it for years. If you have a better way, that's fine. But it stands for strong nuclear, electromagnetic, weak nuclear, gravity, and that's in order from strongest to weakest, and it's in order from shortest range to longest range.
Wait,
Sewage.
what's that one word next to the sewage?
There isn't any. This is blank
the
over.
one to the left on the top.
Shortest range,
Okay.
and then longest range is on the bottom. And which one are we talking about right now?
We're talking about electromagnetic.
We're talking about the electromagnetic force. And one of the truths of the electromagnetic force is that opposites attract. That is, that positive charges, what's going to happen between these two guys?
They're gonna repel.
Repel.
Combined.
What's going to happen between these two guys?
They're also gonna repel.
No, they're gonna go away from each other.
Repel. And then these two guys?
They're gonna come up to each other and make out.
Okay.
Excuse me, what?
We can just have a peck.
Attract. And one of the results of this is that if you generate a static charge, you've done this before. This is you. This is your hair. And you take a balloon and rub it on your hair. You've done this? Some of the electrons from your hair are transferring to the balloon, or vice versa. We'll say it's the first way, though. So now your hair has a relatively... If the electrons have transferred from your hair to the balloon now has what kind of electrical charge?
Positive.
Try again.
Negative.
Wow. And your hair now has a relatively positive charge. One thing it does is that it makes, since all your hairs have a relatively, maybe not all of them, but the hairs that were rubbed all have a positive charge now, and same charges repel, all of them have a positive charge. Your hair's spread out like this, which you've seen happen, like it makes your hair look frizzy. And then the balloon now has a negative charge, and if you bring it close to a wall, which has what kind of charge when it's just sitting here?
Negative. Or it doesn't have one.
No charge. No charge. But what happens is if you bring this negatively charged balloon close to the wall, which is made of what? Is it neutral because it has no charges at all? No, it's neutral because it has a mix of all different charges. But when you bring it here, what does this negative charge do to these negative charges?
It makes more negative.
No.
They attract.
It rids of them.
They repel. So the negative charges that are in the wall get further back in the wall. It pushes them away. And now the wall has, or at least right here, a relatively positive charge. And so the balloon,
Stay there.
yeah, but the balloon attracts to the wall. Have you experienced this before? Have you seen this happen where you rub a balloon, you can stick it to the wall?
I've done this, but with
What?
Did we do a lab about this last year?
Yeah, we did do a lab about this last year. Thank you for
I
asking.
messed up Kendall's head.
There's a similar property. There's a similar property of an electroscope on page 199, kind of like your hair flying apart. An electroscope is a little instrument that looks, it's usually in an Erlenmeyer flask like this. It kind of has these metal leaves dangling from it, and it has this rod on the top that goes all the way through. And if you touch a charged object to this, the charge flows into these leaves. Doesn't matter if it's positive or negative, but now both leaves get a positive charge, for instance, and they
Explode.
they repel, and the leaves separate. So they both get a negative charge. They separate. So what this does is it detects if there is a charge. It doesn't say whether it's positive or negative, but it detects if it is. Could you do it with a battery? No, the battery itself does not. The battery itself does not have a static charge, and we're going to talk about batteries right now, actually. The other kind of electricity,
This one's big.
all of this electricity was what kind? Static. Are we still talking about the electromagnetic force?
No.
Try again.
Yes.
Yes, we are. We're just gonna change subtopics. So that's still true. I'm just erasing it. The other kind of electricity we commonly talk about is current electricity. The other kind of electricity we talk about is current electricity. What does the word current imply to you? Like if you have a current in a river, what does that mean the river is doing? Flowing. Current is the flow of electricity. Is really a topic. We're really talking about the flow of electrons. That's what current electricity is. The flow of electrons is current electricity. And it relies on what's called electrical potential, which is also sometimes called voltage. And it's abbreviated with the symbol V, and it's measured in volts. And this, in the very classic analogy, voltage is like the difference in height of a river. We often liken current electricity to the flow of water. So if water starts out up here and it ends up down here, the difference in these two heights is like the voltage. The difference in the charge is the voltage. So in a battery, there's one charge on one end of it, a positive charge, and there's one charge on the other end. And the difference between those is the voltage. In a 9-volt battery, the difference is 9 volts. In a AA battery, the difference is 1.5 volts. But that voltage difference can be used to power a circuit, like we had at the very beginning. There are two other attributes of the circuit we have to talk about. I is current. I'm just going to write this down in a different way, the way we're used to doing it. The equation I want you to understand and to memorize is V equals IR. So write that down right away. Everyone needs to have that written down. V equals IR. This is called Ohm's law. This is called Ohm's law. Where V, as I just said, V is voltage, measured in volts. I is current, measured in amperes. Your grandpa, or maybe your dad, even if they're kind of an old timer, will call this amperage. Have you ever heard the word amperage? That's the real term is current, but it's measured in amps. And so since voltage, which is really called electrical potential, is measured in volts, we call it voltage. And since current is measured in amps, we sometimes, rarely nowadays, call it volt or amperage. And then R is resistance, measured in, now check this out. This is the Greek letter omega, the capital Greek letter omega. And you that's what we use, that's the unit. It's called an ohm. It's pronounced ohm, but we write it as the capital Greek letter omega. And that measures resistance. Hey, and what is electrical resistance, by the way? What is resistance in general?
Omega?
Resistance is, if I say that, remember we said inertia is the resistance of an object to change its motion. Resistance is something that's kind of preventing something else from happening. So resistance is how much whatever material this current is going to be made or flowing through, how much that resists the flow of electricity. So in our circuit, our very simple circuit with a single load, and a wire, we have some voltage, we'll say 9 volts. We have some resistance, we'll say 1 ohm in the light bulb. And then we can measure the current. Well, V equals IR, we write every time. What are we trying to solve for here? If we're trying to find current, what are we trying to solve for? Now try again.
Voltage.
If we're trying to solve for current, we're solving for I. So we want to manipulate this so that I equals V over R. I equals, what's the voltage? 9 volts. Over R, 1 ohm. What's the current? Oops. Equals 9 amperes.
So
They're usually very simple equations to solve.
what's usually?
Well, it could be more complicated, certainly. Your book also talks about here, one last equation, sorry. We had used this equation before, but now we have a new way of expressing it, and it is P equals IV, where P is power, again, the exact same kind of power that was P equals E over T. Let's write that one again, P equals E over T, because that one does come up again. Where P is power. What do we measure power in? Oof. Watts, thank you. Watts.
Wait, Shylin.
I, as I just said, is current measured in amperes, or amps, yeah. And V is, as I just said, voltage measured in,
Amps.
no,
Whoa, watts.
no,
Volts.
volts.
Is that what you're saying?
And then down here, E, again, is energy measured in, what do we measure energy in the SI?
Joules.
Joules. And then T is time, what do we measure time in the SI?
Seconds.
Seconds. This is an equation from 2 chapters ago. This one is new, but it is made entirely of variables that we are already familiar with, either from previous chapters or from this equation. This is the math for this chapter. You might also, just so that you're aware, you might also be given a diagram of a circuit and asked to solve what is the voltage of the circuit. Like if we are given this one, kind of like this, might be a little bit more complicated, but kind of like this, you'll be given a voltage, electrical potential of the battery. You'll be given the resistance of the load. A lot of times for these kind of problems, we assume the wires have no resistance. In reality, that can never happen. Everything always has electrical resistance. But we oftentimes in these kind of diagrams assume that the wires have no or minimal resistance. And then you'll be asked to find the current, for instance. Or you might be asked to, it might tell you the current is measured with an ammeter to be this. What is the resistance of the load? Do you have questions about any of this? We're running short on time, but do you have questions? 2 things we didn't have a chance to talk about. Parallel and series circuits. Look up the definitions. And the other thing was... electrical conductivity and resistance. We did talk about resistance, and conductivity is just how well the electricity can flow in a substance. So those are all definitions. Make sure you look those up. Any other questions?
Video as a big group and say bye.
Okay, say it. Everyone say bye.
Bye.